So welcome everybody to lecture 8 in the class. So it means we're halfway through. Seems like it's gone very fast for me. I don't know how it feels for you. This is going to be part 3 on within host viral dynamics. And I did want to give people some time to review where they are on their projects as well. So we'll see how far we get today. We're going to continue our topic of modeling immune response, thinking about that. We actually had a very nice lecture from Bart Ehrmantraut earlier today about how to do that, which could have been very helpful. And we'll talk a little bit more about limiting cases. Let's see how far we get today. I wanted to go over some of the homeworks because I think there were some issues people had with the homework this time. And I would like to do these as exercises. So I'd like everybody to boot up Tellurium on NanoHub, or if you're running it locally. And I'd like to go over some of the homework assignments. And I think pretty much to everybody, I said that if you wanted to take a little more time and redo the homework from this week, the homework number 5, and resubmit it, I'd be happy to regrade it. You don't have to do that, but I'm going to cover some of the issues. So the first homework problem was we compared the stochastic model to the OD model. And there was this plot from this paper from Penn State, which looked at the probability of extinction of the epidemic if you started from a single infected individual as a function of R0. That's the basic reproductive rate. And when we ran the simulation using the Gillespie algorithm, whether the Gillespie algorithm was the right one to use or not, I don't know. I believe Alessandro Vespignani gave a seminar, I think I sent a link to. Unfortunately, I had a time conflict today in informatics on doing the stochastic modeling properly using agent-based methods. So there was actually a talk specifically on how to do this correctly today here at IU from a very famous former professor here, one of the early professors in the School of Informatics, who moved on to Northeastern later on. But one of the things that we discussed was that in reality, even if on average R naught is 5, some people who get the disease may give it to nobody, and some people may give it to 200 people. R naught is the average number of people you give it to. And the actual way the disease spread will depend on the specific outcome, not just on the average in reality. In particular, if you give it to nobody, the chain of transmission dies out. And so if you start with a single infected individual, it's possible they don't pass it on to anybody, or they pass it on to 1 or 2 people and they don't pass it on to anybody. And so in that case, you don't get the dynamics that you might expect from the ODE. And in this example, R naught is 5, 4.9, so it's pretty big. We have a population of susceptibles of 1,000. We start with 1 infected individual. And most of the time, people get infected, and essentially everybody gets infected. But we see this one line up at the top where nobody got infected besides that first person. And that means in that particular case, that infected individual recovered before they passed it on to anybody else. And so the question was, given that model, what's the probability that they don't pass it on, or at least don't pass it on very much, as a function of R naught? Clearly, if R naught is less than 1, on average, you pass it to fewer than 1 person. So typically, you don't pass it. So typically, the disease becomes extinct by itself. The bigger R naught is, the less you expect to pass on. I mean, more you expect to pass on, the fewer extinction events you expect. But there's this range of R naught between 1 and 5, where you get a very different outcome here. In the OD model, you get extinction for R naught less than 1, and you never get extinction for R naught bigger than 1. In the real world, for R naught between 1 and 4 or 5, it's possible that that individual doesn't infect anybody and you get extinction, or only a few people get infected and extinction. This is why track and trace can work. If you didn't have this, track and trace wouldn't do any good, because by the time somebody's infected somebody else and it's out in the community, it's going to be everywhere. So this is basically the justification for these track and trace approaches. And I asked people to calculate how the probability of extinction depends on, I said mu and the total population S naught, but first R naught. And I don't think anybody did this. And there were various reasons that people had trouble, but I want to make sure that you understand how to do it, because it's something you're absolutely going to have to do in projects. And it's something that you're going to have to be able to do again and again as we go forward in the class. And so it's critical that we be able to do it together. And so what I'd like people to do is you could load the SIR model that we built before. Josh, do you remember where that is?
You mean the Gillespie?
Yeah, that one.
That's in lecture 5 demos in the Google Drive.
So I'd like everybody to load that and get it up. I don't want to go forward until everybody has it.
I'll post the link here in a second.
And I sort of want to hide what I have here because frankly, it's the final result isn't the thing that's so interesting here. I want us to work through how to get there.
I'm copying the link now in the chat.
So the first thing, does everybody connect? I want everybody to have this base model up on their computer.
Got mine loaded.
Okay, great. Anybody else need it? And I know, Mercedes, you said you don't have a computer, so I'm sorry if you can't, if it's hard, it can't for you to do that.
I should have it back tomorrow.
If you need help catching up on things, come to me or to Josh, and we'll do our best to help you out. Losing your computer is no fun.
No, it's a really bad year for it to happen too.
Yeah, internet and computers are much more, I mean, they were always important, but they've gotten to be sort of life critical at this point. Okay. So what I'd like, so does people have this working? So now what I'd like to do is run this as a Gillespie. So I'll do S equals P dot Gillespie. Let's see. Type it right. There it is. So we'll run this as a Gillespie simulator. And we'll plot it. And this particular set of values that I picked, nothing interesting happens. And let's actually calculate what R naught is. So R naught is n times gamma 1 divided by mu. So let's get what R naught is for this simulation. And let's put the value of R naught in our plot. And I'll put what I know I want for the plot. You don't have to do that. You're welcome to if you like, but you don't have to. Can I get there? Oh, I didn't know that show. Okay, did people get something look something like that? Yes, no? So I want to make sure everybody's able to run the simulation and see what it does. And let's actually run it multiple times. So that we can see how it looks when we repeat it. So let's run it a couple of times. And I certainly don't want to run it 1,000 times. So that's 10 replicas. Okay? So I'd like everybody to try doing that. And there were, some people did this. Some people had trouble with this. When people had trouble with it, they typically forgot to put the reset into their simulation. And if you run a simulation, if you do call the solve repeatedly, it will continue from where you stopped. It won't reset the values. So if you want independent runs, you have to have the reset.
My model looks the same as yours, but I'm still getting the two horizontal lines for S and I in all my graphs.
Huh. Okay. Let's see. What's the time range you're running over?
0 to 40.
Okay. And is it possible that you did somehow was not set to be 1 at the beginning?
No, it said it was 1.
Why don't you try setting it to 10, see what happens.
Same thing.
Same thing. What about other people? What are other people getting?
I get something similar to yours.
Okay, anybody else?
Mine is similar to yours.
Okay, and what's the value, Kali, what's the value of R0 that's being printed out here? Kali, what was the value of R0 that you were getting?
2.5.
2.5, so the same. Well, I'm not sure what to do. I mean, if you want a screen share, we can take a look at it together and see if we can fix it, or we can try to do that later. It's up to you. I'm happy either way, because I think it'll be sort of boring if the next steps will be boring if you can't if it doesn't work. But I'm puzzled why.
Oh wait. All right, I figured it out.
Okay. One thing, and this was a question that I had from a couple of people that I will remind you of, is that one thing antimony is not friendly with is that if you have a reserved word inside of your model definition, it will usually throw an error, but the error may not be very informative. Like it may say unexpected parenthesis or unexpected equal sign in line 29. And so if I come here where I have gamma 1 equals 0.1, the word gamma is a reserved word because there's something called the gamma function. And so if I wrote gamma equals 0.1, I would get a strange error. And occasionally there are reserved words that don't throw an error but don't work. And so it's possible that that can happen. It's also very easy to do something. I know one person had some problem with code where they had typed a minus sign instead of an equal sign in one of these lines. Again, usually those will fail on parse. Those will fail when you do your load, but sometimes they don't. So, okay, good. Now, if we look at this and we really wanted to see how this is going to play out, we'd really have to run it longer than 40 time steps. So maybe we should run to 60 time steps here, like that, to let it finish. But what we see here is that there really is a difference. Sometimes it gets infected and it comes down a lot, and other times it stays up at the top and doesn't do anything. So what we want to do is count, as we run through our loop, we want to count how many times we had nothing happen and how many times something happened. So we could do that in fancy ways, but let's just do it in a dumb way. We'll say count equals 0. You can try this on your own in your own way. Count equals 0. And then I'm going to do my run. And it would be if the final value of S, m dot S, is greater than, we said our tolerance was 85%, I think, right? Josh? 0.85 times our initial value of S naught, m dot S naught, count plus equals 1. So that's keeping track of how many times the thing failed to infect. And if somebody catches me doing something that's silly, let me know. But let's try to print count and see what happens. So 2 of the times I ran it, I stayed at the top, and the rest 8 of the times I didn't. Let's try running it again, see if I get the same number. This time I got 5 replicas that didn't work. So each time I do it, it's going to be slightly different. So can everybody get that working? So now I know for the particular value of replication that I've got, the particular number of iterations I've got, and particular value of R naught I have, this failed to infect that many times. All right, does that work for people? Does it make sense? Because what we're trying to calculate is the probability of failure as a function of R naught. So first thing we have to do is see what happens. Then what we're going to do next is calculate what our probability of failure is. And since I made itotal a parameter, the fraction of failures would actually be count divided by itotal. And if I want that to work and not do something strange, probably count better not be an integer. So let's make count a real number fully. Okay, so here 0.3 of 10 replicas were failed. And if I wanted to try running it for 100 times, it'll take a little while. 39% of the time it failed. So I want everybody to try to make that work. So this is problem 1. So I want to walk through it so everybody has that. Because I want to go through the steps of that problem. Because this is something that as I say, these are steps we're going to need to do repeatedly, and seeing how to go step through a problem to solve it, I think is important. There are many ways that you could do the same thing. It's not that you have to do it this way, but I want to show you one way that works. There might be more elegant Python-y ways of doing it. This is sort of a procedural way of doing it. Okay. So now, for any given parameter value, we can calculate what the fraction of successes or failures is. So the next thing we need to do, we said now we want to change our value of R naught. And we could change our value of R naught by changing n, by changing gamma 1, or by changing mu. Let's do it by changing n. So we'll put a loop in here for n in, I prefer using n pi a range, but you can use range if you want. N pi a range, and we'll say, and we want n to start out, let's see, 2.5 corresponds to n of 5. So R naught is half of n. So let's start with R naught being something like 0.2. And let's have it go up to 5. In the graph here, it goes up to 5. Let's make it go up to 6, say. And we don't want it to be too fine resolution, because to begin with, we're just getting a rough sense of how things go. That's another thing to do. When you start out, you can make your graphs and things rather coarse, and then you can increase the number of replicas and the number of detailed points once you've got your code working. So we'll make n in a by a range. We'll have to indent everything here. And now we're going to have to set, after the reset, we'll have to reset m dot n to equal n, because otherwise we haven't changed our value of R. And when we print, let's print here R naught, comma, count I over I total. So now this is going to print out the values that would correspond to this graph. Okay, try that. Everybody try that. See, if R naught is very small, it always fails. R naught's just a bit above 1. The way we've defined it is probably counted as a failure anyway. We could make our constraints a little bit clearer. 1.6, it's very clear. Either you fail or you don't. In this one, it's a bit harder to make out. And as R naught keeps going up, we still see there always are some failures, even if R naught is quite large. All right. Okay. People have that working? Anybody need more time on that one? Okay, so the next thing we want to do is we've now calculated R naught versus the fraction of failures, which is the information in this plot. And so now we want to plot it. And again, there are a whole variety of ways one could decide to plot that information. I tend to use this perhaps not very pretty VStack approach to calculating the plot. You could also create a list and put it as then plot the data as a list. But I'll do data equals npi empty parenthesis, and let's see, 0, 2. Is that right, Josh?
You need another parenthesis because it's supposed to be a total. Yeah, you got it right.
Okay, and then so this gives us a placeholder to put our data that we're going to plot in the form of an MPy array. And then when we do our print, we will also add it to our array. So we will do D equals npi vstack. Stack. You could also do a append if you had made it a list. npi vstack, and then let's see, it's parenthesis, and then we need to add it. So if we add it as a tuple or a list, and then remember, our 0, count divided by I total. See if that works. And instead of printing this, when we're done, we can now print D. See if it worked. Oops. Typo. VStack. One positional argument, but 2 were given. I have it correct here. Oh, extra parenthesis. Typo. And pi stack. Oh, and the parenthesis. The argument for that is not the most friendly one. Okay, let's see what we got. Okay, so these are the data that should make up this plot. So does everybody have that working or not? And again, you're welcome to do it a different way. If you want to use a list, you want to do it as a fixed size array, any way you like. But the idea, what I'm trying to walk you through here is the idea of you plot your values and you see what it does. You define a selection criterion for when you've got the thing you want. Then you check that that behaves properly. Then you put that inside a loop that changes the parameter value. And you check that the parameter value, comma, the thing you want to calculate look right. then you assemble those data sets, those data pairs into an array, any way you like. And finally, you plot it. And so now, people who need more time are welcome to keep working on this. But the last step of this exercise is now plotting this instead of printing it. So I can comment out my print statement, and I can do an my m dot plot here, grab my m dot plot. And this time I'm going to do extinction versus R naught. And I'm going to not make it show false. I'm going to make it show true. Here, the x-axis is R naught. The y-axis is extinction probability. And I need to plot, this is wrong, not plot. I need t dot plot array. And I need to plot d. And for some reason, X title and Y title are X label and Y label in plot array. It's annoying that they have different names. But you could, why don't we just leave out all the details here for a moment? So since you wouldn't be expected to remember that, let's just do d dot plot array of d. Try that. Oh, I have to put, and I've set it up so it's actually going to take quite a while because those extra plots are going to be slow. Okay, there's our result.
Do you have any advice if Jupyter Notebook is just spitting out that bottom line and not the actual graph?
So Jupyter Notebook spitting out that bottom line and not the actual graph. Let's fix this. Let's turn off this plot, which is taking quite a bit of time. And for debugging, we could make the number of eyes we run 10 instead of 100, so it runs faster. So let's run that again. Won't be so pretty, but that's what we get. So you're getting this matplotlib lines thing here, but you're not getting t plot array displaying. Is that right?
I hadn't commented out the te.plotarray. Let me just try te.plotarray d.
Yeah, try that because it may be there's a typo in that.
Okay, yeah, that's showing the plot. I have multiple different lines though now, so I'll try to debug that.
Multiple lines meaning?
Yeah, like multiple.
Did you comment out this piece here, the plot up from above before?
Mm-hmm. Yeah.
I have one singular line, and
One-
it's shooting up from 2.5 upwards, which is kind of interesting.
Okay, do you want to show us that? Okay.
Sure. Let's see. Give me a second.
I mean, on the one hand, if we walk through this, it only takes a few minutes to do it. On the other hand, if you haven't done it all the time, it's not easy to do.
Ryan, try changing m.n equals n in your inner for loop, because I was having that same issue.
This one right here.
No, like below reset all, have a line that changes the value of m.n to n. That should do some, yeah, because I was having the same issue.
Okay, that's a lot better. Yeah.
Okay, great. Okay, good. Is
Thank you.
anybody else having problems with this? Anybody else? Everybody? Okay. Okay. So now we can actually try to make it prettier. So we could make our interval for n smaller. And we could make our I total bigger. And this may take a little while to run because we're running a lot of loops. If it takes too long, then we can. Maybe 0.1 was too small. Okay. So if I were to change my axes, so I could make the vertical axis go between 0 and 1 instead of auto scale. If I look at my bottom value here, it's about 0.2, isn't it? Which is the bottom value here. It's 1 up till 1, and then it comes down. So I've actually replicated this result essentially exactly. Now, that was the first part of the homework problem. Now, what you'll find is if you change the number of replicas here in this line, you'll get more or less jagged lines. The more replicas you do, the smoother the line will be. You could change the detail here. Maybe 0.1 is a little bit too fine a resolution, so let's make it 0.3. But let's run a little bit more replicas. And we can talk while it's running. But this now basically solves the first part of the homework problem. But again, what I'm trying to get through across is the steps, which is that when you have a problem like this, you don't solve it in one go. And you can once you're very familiar with how to do it. But there's always a set of steps you should think about, which is not trying to do it all at once. First, plot the data sets, the time series for the parameter values you've got, and make sure that they're working. Secondly, if you're iterating, so you're doing multiple replicas, make sure that when you iterate, you get something reasonable. Because it's very easy to leave something like an m.reset all out or an m.n equals n out. So you want to catch those things. Once you've got that working, you have to do what I'd call a metric, which is how do you assess the question that you're trying to address? In this case, what's the fraction of replicas which die out? And so in this case, we said we define die out if fewer than 15% of the individuals who are susceptible become infected. We could change that number. We could make it, here we got this smoother curve. What if we made this number 95%? What would happen? That would be changing our tolerance. We expect now that the fraction that we count as extinct will be lower, but how much lower? That would be something interesting to do. And typically, whenever I'm developing these things, I start by printing out the values. And it's only when the printout gives me what I know is right that I worry about putting into a VStack and plotting it. Because it's much easier to understand what's going on when you actually have the numbers in front of you than when you're looking at the plot. Didn't make a big difference, did it? 95%, 85% didn't make much difference. Maybe a little bit. So now you could go back and change mu, total population S naught. I can tell you as you make S naught bigger, this curve will get smoother and even more like the curve in this plot. I can also tell you that the time it takes for your simulation to run is linearly proportional to S naught. And so if I make S naught 10 times bigger, it'll take 10 times longer to run. And therefore, you want to do these things for relatively small values of S naught first, because Gillespie is proportional to the absolute time is the absolute number of replicas you have. And therefore, before you run your production run to get a beautiful smooth curve where you set S naught to be 10 to the 6th, which is going to take an hour, you make sure everything runs this way. Okay? So does that help you think about how to solve a problem like this? I hope that helps at least a little bit. And so we have a version of this code now available to you, homework 5, exercise 1. And if people want to go through it, play with it a little bit, modify it, maybe make it prettier, run the second part of the exercise. And again, you don't have to redo the homework, but if you want to, I'm happy to grade it for next week. Okay, questions about that? Somebody's still showing needs more time. Does somebody need to discuss something, or is that have you solved the problem? I guess I can re-poll. You don't have to put your hand up and say I need more time. You can answer me this. Everybody got this?
Yep.
4 people out of 6 people said they've got it. So I don't know who somebody's not answering one way or the other. So, okay, 6 out of 6. Okay, and Mercedes, I know we can go back over this if you want. Okay. All right. So that was the first problem. And again, I understand that doing this from scratch is time consuming. But I also want you to see that once you've gotten used to it, it's not that time consuming to do these problems. And of course, that's tricky because, of course, once you know the answer, it's easy. Before you know the answer, it's hard. And so I'm not saying that it doesn't take time to figure it out, but I'm hoping that by practice, you can get more familiar. Okay, the second problem was on the BSIRD model and the BSIRDS model. Some people had trouble writing those models and getting them to work. And some people did some work trying to figure out, at least by hand, what the intervals, this oscillation frequency was. And what nobody did, which is what I was hoping that was asking you to do, was actually calculate that. And the code that we've just written here actually does that quite effectively. And so we can take the code that we've got here and we can turn it into this model. And so I'd like you to do that. I'd like you to take the model that we just wrote here and modify it to implement the B and D terms. And we can do that together. And then I want to go through exactly the same steps we just went through to generate a calculation of the oscillation frequency versus the R0. So again, we're going to do this in steps. We're first going to generate this plot. And so to generate that plot, we have to modify our equations a little bit. We have S goes to I goes to R. Those are these terms here. Those don't change. We have to have a birth term. So we'll add E0, which is nothing goes to susceptible. And the rate law is B times S plus I plus R. That's the birth rate. Okay. And again, I want everybody to follow along on your own code. All right. And then we have to have some deaths, and there's going to be 3 death terms. We're going to have our B's, our S's die, which is S goes to nothing. And the rate will be D times S. We'll have I goes to nothing. And the rate is D times I. And we'll have R goes to nothing with a rate D times R. Okay. And now we have to define 2 new parameters, which are the birth rate, B. And I said that that was supposed to be 0.01. Which, by the way, is ridiculously fast unless you're a cat, maybe. That's saying that women give birth every 100 days, which is nuts. All right. And then actually twice that, because we don't have a gendered population. So the actual birth rate would be half of that. So cats are about right. I mean, gestation period of 50 days, and they're always pregnant. Doesn't make these numbers aren't meaningful. And then a death rate, which I also set to be 0.01. Which is also crazy because it means your mean life expectancy is 100 days. So I don't know what kind of animal that could be. Maybe a possum, but definitely not a human. All right. And now we're going to load our model, and we'll do our reset, calculate R0, and we'll plot our results. Actually, we don't need this for the moment because we're not changing that. So we'll calculate R0, and we'll plot, and we're not going to use the Gillespie here. We're just going to use simulate. And Josh, what was, and the time scale, we were going to do 500 days. And we'll use, say, 2,000 points. And for the moment, we'll plot everything. All right. And we'll just do a m.plot. And the show. Does it break? To stop Python? I don't remember. I think break. So it doesn't run the rest of it. Okay. So I'd like everybody to do that. All this stuff from here down isn't doing anything at the moment. while you're working on that, I'm going to grab this slightly fancier version of the plot. So my plot is labeled. But does the same thing. Oops. There. Well, I have a syntax error from break, but it does the job of stopping it from running. So that works. Okay. So now that we've done that, the next thing requires a little bit of thought, which is what we want to do is we want to find the time between the peaks. Does anybody have a suggestion for how you could find the time between the peaks? Well, what's special about a peak? What defines a peak?
The first derivative switches signs from positive to negative.
Fine. Perfect. So if I have a value which is bigger than the one before it and bigger than the one after it, I'm at a peak. Now, if my spatial and temporal resolution aren't good enough, I might have something that's really flat at the top, and then I'm unlucky. But unless I'm unlucky or sloppy, if I look for places where the value is bigger than the value before and after it, I found a peak. If I'm unlucky, I could look at the value a few times before and a few times after and find the peak that way. So why don't you, everybody think about writing a little code that goes through S and finds the position of the peaks, the times of the peaks. And I'd suggest that one thing you can do that's convenient, well, actually you can iterate over the elements of well, there are a bunch of ways to do it. Why don't people think about that for a minute? So what I want you to do, and let's just say we're going to use, I mean, we could use any of these time series. They're all giving us the same information. I would suggest using R as the one you're going to find the peaks for. So what you want to do is you want to go through the time series and find the time at the value at which R's are locally maximal. So take a few minutes to think about how to do that. And I'm trying not to be like Julia Child. In other words, I've done these exercises, but I'm not, with the exception of copying some plot labeling things, I'm not pulling out the solution and showing it to you. I'm doing it on the spot. So I'll start again. I mean, so just take your time to think about this. And if you have any questions, feel free to speak up and ask. Thank you. And if you need help thinking about iterators, there are a couple of ways you could iterate through the data set. You could actually iterate over the data set itself, in which case what will be returned to you are the elements of the data set. Or you could iterate over the index. Personally, I find iterating over the index a little bit easier. And so if I were going to do this, I might say for I in range of the length of S. And that will let me iterate line by line through the data set. The other thing that might be useful to know, if we're going to do this, is we could set, let's see, time equals S. And this is something that Josh uses a lot that I tend to forget about, that if we do time like that, time should now contain just the time column. Is that the right syntax, Josh?
Yes, except that is square bracket.
Square bracket.
And then you have to specify it in the simulate.
So that's what, that one's a little trickier. So let's do this. So we'll do s dot time, and then the simulate will do time. We said we're going to look at R, right? And so let's say, let's call it, say, something like time list, so we know it's a little bit more obvious. Time list, R list equals S. You can also use slicing to get this information out, if this is convenient. And in fact, before we go to the for, one of the things we could do is just print these so we see what they look like. And if we're going to do that, maybe we don't want it to be quite so long, so let's shorten it just so it's clear what we got. So you see here the times, and here are the values. All right. So now we can iterate over our length. And what do we want to do? We want to find out where we have a local maximum. And let's create a placeholder for holding that list of local maxima. So let's say something like max time equals, it's Python, so everything is always going to be a list. So we create an empty list. And now what we're going to do is we're going to go through our iteration here. And we'll look for what was suggested, which was if our list sub I is less than our list sub I plus 1, that means that we're going up between I and I plus 1. And our list sub I plus 1 is greater than our list sub I plus 2. Then we're at a local maximum, aren't we? Then we could say, okay, we found our local maximum. That's I plus 1. So then we could do T time list dot append the time for I plus 1. Sorry, I said time, max time, sorry. Max time dot append the time which corresponds to I plus 1. So it would be time list. Time list square bracket I plus 1. So that's, we'll have now a list of all the times at which we were a local maximum. This will crash, by the way. Why will it crash?
Because once we hit like the second to last index, then we're like, once we add like 2 or 1, we'll hit the end of we will go off the array.
So we better do a -2. And let's just do a print at the end of this. Again, I'm big on prints rather than plots to begin with. Let's print time list and see if it makes any sense. And let's put that break isn't really right. I think it's probably stop rather than break. I should use variable. Oops, I still have my. Is that not wrong? It's printing a lot. So, did it not work? Why not? So I get time and R. Oh, because I didn't put my time range back. The time list should still be time list. Oh, because I put time list on max time. So let's look at what we got. Everybody try this before you look at the results. So what we're doing is we're not using this empty thing here. Sorry, we're not using, that's not there, we'll stop. So we're going to do, we plot our picture. We create an empty list to put our list of top peaks in, peak, peak, peak. We create a place to put our time. We create a place to put the values. We iterate over all the elements in our list. And we say if an element is bigger than its previous one, and bigger than the next one, then we append the time that corresponds to that to our max time, and then we print the max time. And if we're lucky, that should give us this point. Oops. I have to do annotate. That should give us this point, and this point, if we've done it right. And then we can measure this distance and this distance. And that should tell us what the period is.
Mine's throwing an error that says when I'm trying to define time list and R list, it will only take integer or Boolean arrays or valid indices. Like it won't take the comma time or the apostrophe time.
You gotta make sure that you specify it in the simulate.
I do.
Okay.
You want to show us? We can definitely take a look.
That would be kind of hard because I'm actually doing it on a different machine than what I'm zooming on.
Okay, sorry.
No, that's my bad.
So say again what's happening there. What's the error you're getting?
Here, wait,
So
maybe
you could paste the error. You could paste the error into the chat, I suppose,
Or the code.
or the code.
can I just show you my screen? Does that like
That works too. So you're getting the oscillations just fine, but boy, I cannot read the error. So you're getting the first part okay, and so when you're where is it crashing?
It's crashing when I define time list.
So when you say time list equals S square bracket quote time close quote, that crashes.
I think it has to be time with a lowercase.
Oh, here?
Okay.
Yeah. Yeah, unfortunately, Python cares about capitals. So the key does have to match. So if it's if you had uppercase time in here, it wouldn't work.
That worked.
Yep, that fixed everything.
Right, because in Tellurium, time with the lowercase is a reserved variable, and that's the one you're referring to when you.
Okay, that makes more sense. Thank you.
So did you get this plot 46, 179, 301, 421?
Yep.
Great. Okay, so I think let's look. 46 seems about right. 179 seems about right. 301 seems about right. And even this 421 seems about right. So that's given us the points of the maximum. So now what we want to know is the intervals, the time interval, the period. And there's a NumPy trick for that, which I wouldn't have known, but Josh knew, which is intervals equals npi.diff of max time. Is that right? Syntax, Josh? So diff will take if you have a list, it will take the space, it will calculate the value of the first one, second one minus the first one, the third one minus the second one, the fourth one minus the third one, and so on. So that's very convenient. So now, but you could also iterate through the list and do it by hand. I can now print intervals. And now I have 133, 121, 120, which is the period, the distance between the first peak and the second peak, the second and the third and the fourth. Because remember, the question was, what is the time scale of the oscillations? So that's what we're measuring. And the next thing that I do is I can average that. So period or interval, just say period, it's easier, period equals NPy dot mean of intervals. And again, NumPy has lots of functions and nobody can remember all of them, but if you go to the NumPy manual, you'll find lots and lots of convenient things to do. Of course, you can also go by hand. I could iterate over it and find the average by hand. So now let's print period. Okay, 124. So that was the answer for the first part of the problem. Now, I want to use the code that I wrote here to see how that value that I care about changes as a function of various parameters. So I said, what happens on parameter values? So let's just do one example here, and then you can now go and home and try it on your own. Let's change R naught. Let's see how it depends on R naught. So I'll grab the code that I wrote before, and I will wrap everything here in that code. So I'll do for NPy in A range. I don't need my count or my I total or any of this because I'm only running it once. I'm not doing stochastic anything anymore. I need to do my reset. I need to set my value of n. I need to calculate my value of R naught. Oops. And now I have to indent this stuff. Sorry, I gotta get rid of a lot of stuff. I don't need this plot. I don't need the show. I do need to indent all of this. And now let me do my append. Except that instead of appending count over I naught, I want to append period. And now I can get rid of all this stuff down to here. So maybe I want my plotting labeling. Oops. I made a mistake. What did I do? All right, no, well, I forgot to take my prints out, but there it worked. So do people understand what this plot shows? Somebody tell me what that plot shows. I haven't labeled the axes, but look at what I've calculated. What's in my stack? Somebody? The first element of my stack is R naught, and the second element is the average period, the average time between the bumps for that value of R naught. So if I now use my fancier plot function, it would be period versus R naught. The Y label would be period. And the X label should be R naught. And let me not print all this stuff, which is not very informative at this point. So this is what I asked for. This was, how does the period change as a function of the parameter? In this case, we changed R naught. I want everybody to take a minute and try to catch up with that. And we can get rid of the commented out stuff, so it's simpler to look at. And I'm sorry that's running a little bit off the screen for the plot, but we don't really need all of that information. This error that's throwing here is because if R naught is less than 1, there are no bumps. And so then this list is empty, and it's trying to do a calculation on an empty list. So if I set my initial A range to start a little bit bigger than 0.2, I should clear up that error. That's what that error is about. I could fix that by having something that said that if interval is empty, I don't do these calculations. Fortunately, Python is forgiving, and so it's not causing a problem. Okay, if you've already got it, why don't you try changing one of the other parameters? Instead of changing n, you could try changing the death rate, for example. So let's try that. Probably we need a different initial n. We need something a little bit bigger if we want that to behave properly. So let's make it something like 9. And then instead of changing n, let's change d. So our death rate could go from, here was 0.001. Let's make it 0.0001 to point. Really be better to do this logarithmically, wouldn't it? 0.01 this will be the same. We have to change, in this case, we have to change D. this. Yeah, that didn't work. So I outsmarted myself on that one. That one I'd have to play with more. And the way to do it would be to go back and look at the simulation output and make sure that it didn't do something strange. So when my death rate is too small, my population just keeps growing. So there are no maxima, local maxima. So that was a poor choice. If I start with my death rate being 0.1 and go up to 0.1 there, then again, the first one oscillates. The others have everybody die out. So that's not so interesting. If I balance my birth rate and my death rate, I suspect it'll be more interesting. So now it does oscillate. And so now I actually get something meaningful. So my goal here wasn't to make you go through every possible set of parameters, but my goal was to give you something that allowed you to calculate the time interval. And now it's up to you, as part of the homework problem, to try changing what parameters you change and see how these oscillations change, okay? Let me undo the changes I made, put it back to the R naught one. And let's do one last thing. The second one was make it something where you also have where the susceptibles go back to being, the resistance go back to being susceptible after some amount of time. And I may have outsmarted myself on this one. There should be a range of parameters where the oscillations persist, where they don't die out. But it's possible the way this equations were written doesn't work. So if I want my resistance to go back to being susceptible, I have to write R goes to S. And there has to be some rate, and that would be recovery or something like that. Or it'd be loss of immunity. Let's call it loss. And that would be times R. And a lot of people did this just fine in terms of the loss max would be a key reserved words. Let me call loss one. Make sure I don't write something. And that should take a long time, at least 100 days, if not more. So this was now that BSIRDS model. So let's see what happens when we run that. Doesn't look very different here. Let's actually print out the plot for some of these after I simulate. So these are not oscillating. Starting to oscillate here, and the oscillations turn on. And you notice the oscillation period gets shorter as what? As as my R naught goes up. I could also do something which would be maybe more interesting, which would be to calculate the value, the decay time. So if I look at the, and I'm not going to do this here, it would take a little bit too much time, but this is something I would hope you could do in the homework, which is we found the time between these peaks, but we could also find the values of these peaks. And that gives us the time scale over which this oscillation decays. And then I can calculate, as a function of the same parameters, the time scale over which the oscillation decays. Let's do that very quickly. In this case, let's actually just do the interval. We have time list, which is the times. Let us also calculate, sorry, max time. Let's do max values. And we'll now do max vals dot append R list square bracket I plus 1. So I now have the values of the peaks successively. And I can do the same differencing that I did before. So I had intervals equals NP dot difference. I can do, I don't know, peaks, deltas equals NP dot diff of max vals. So that gives me the difference in height between this peak and this peak and this peak and this peak. And the exponent would be the logarithm of the difference in this guy divided by the difference in time. And I'm not sure, can I take a log of a NumPy array? Does that work? So in principle, exponent should equal, is it npi.log?
Yeah.
npi.log of deltas divided by npi.log of intervals. And let us get rid of the V stack here. What I'm trying to do is calculate the decay time of this thing. And so then mean exponent equals npi dot mean of exponent. And let's print period, and let's print mean exponent. No guarantees that this is going to work. This is going to be more of a better homework problem. Invalid number in scalar, not number, not number, not number, not number. So there's a period, but it gave me not a number for my logs. So I have to play with that a little bit more. beneath the print the deltas before I do anything too ambitious for that. Oh, because they're negative. That's why. So I have to take the minus. Let's do this way. There you go. So now you can actually calculate the decay time for this oscillation. I have to play with it a little bit, but you can calculate the decay time for the oscillation and then see how that decay time changes with the parameters. And that would allow you then to answer the question, how do you go from a case where you have the decay disappear and where you have the oscillations disappear to one where you get stable oscillations. And I'm sorry, that took more time than I wanted to. I didn't want to drag you through too much of that, but I did want to give you an idea about how to deal with this. So that last part of the problem was more challenging. Finding the time interval, though, I hope you can do now. Questions about that so far? We'll have this code available to you, so you'll be able to look at it if you want. Okay, question 3 was find some experimental data on viral load dynamics. A couple of people had trouble with that. If I just go into Google, type time series for viral load, and then the name of some disease, almost any disease, and then go to images, I find time series. So I know sometimes finding search terms is a pain, but they're there. Some people found them for HIV, some of them found them for HPV, hepatitis C has them. A whole variety of different examples are available. The second question was a little bit, part of this question was a little bit more, which was, does the viral load curve have the same shape and regimes as influenza virus? Some people did that very well. In general, most of the viruses people looked at had very different curves. And that was very helpful. And then the last question was, once you found the curve, defined its regimes, the question was, what were the times, levels, and rates of change of each regime? And some people had a little bit, either didn't try that or didn't had a little trouble with that. What I was hoping people would do would be at least estimate, and depending on the data set, it was more or less reasonable to do that. Some people found data sets that didn't let you do it very effectively. But for example, with HIV, which was a virus that some people picked, HIV has a very complicated time series. You initially get some latency over a couple of days, then you get a very rapid increase in viral load, really rapid increase in viral load over a period of a day or two, maybe 3. And so then you would have do the same kind of thing we did before, which is how many factors, a factor of 10 takes how many fractions of a day to go up. Then the viral load comes down very rapidly. with HIV. And again, the peak value, the days at which the value peaked, and then the exponent would be the things to get. And then it stays low for a long time. And then you get cycles where it breaks out and then goes down again and breaks out and goes down again. And those are typically on timescales of weeks or months rather than on days. So HIV has a very complicated viral load curve. The initial response being over a period of about 2 weeks, and then the later response being over months and years. Hepatitis C has a fairly short latency, goes up a little slower, then comes down, and then never goes away, stays high for the rest of your life. So that one's sort of interesting. And people found some other viruses that had very different ones. Some people did SARS-CoV-2. SARS-CoV-2 is essentially a monophasic response. The problem is, at least in humans, that there's almost no data on what happens early in the infection because the viral load is near its peak by the time people are diagnosed, unless you're very lucky. And therefore, what you typically see is something where your curve starts when things are already pretty late. So you'll see, if this axis is time, you'll see the viral load starts up here, goes up, and then comes down fairly smoothly like that. In some individuals, it doesn't do that. It levels off. Sometimes it comes up again. If you're going to die, it often comes up very high. So relatively complicated things, but it's the base result, as far as we know, seems to be monophasic for people who have mild infection. So there's quite a bit of interesting data on that. The problem is you never get the early response because you're not diagnosed until there. In animal models, they maybe have the early data. And so I think it's really worth looking around and seeing what's out there. And again, it doesn't have to be in humans. It could be in other species. It doesn't have to be in intact animals. It could also be in vitro. So I think that one is worth spending a little bit of time on. And then the last one was on homework 5. Homework 5 question was question 4. And I had asked people to, this is actually, I'm going to blame Josh on this one. This is a problem suggested by Josh. And it was to look at one of the models that were in that little review paper I passed to people, and to try to implement them and plot the time series, explain what you see, and then see how it compares to influenza. And in the particular case that in the last part, it was looking at the role of interferon and how that worked. And a lot of people didn't try that problem. I really would like you to try the problem because it's critical if you're going to do a project that you'll be able to look at a set of differential equations or a diagram, like the one we just did for problem 2, and write that in the form of antimony and get it to work. And 1 or 2 people had issues with typos in the antimony. So if you type I0 -1 instead of I0 = 1, that'll throw an error. A few people had problems because they gave a variable name a reserved word name. That'll throw an error. And so one has to get familiar with that. But I think it really is important that we be able to do this. And if we're going to try to do another replication exercise in class, having gone through this on your own, I think is really important. So why don't we're over our break time. So why don't we take a 5-minute break? When we come back, those of you, I know not everybody's going to be able to do it today, but I'd ask people to have some results to show for their projects today. And so people who are ready for that, we'll do that briefly. And then we'll go back to the exercises that we were working on in class. If you are not ready this week to show something, then you really need to be ready next week. So, and I'm not expecting a lot, but I am expecting that everyone have some working model to show. Doesn't have to be the full replication of your paper or papers, but to have something that you've been able to put into antimony and run by ideally today, and if not, by next week. So I don't know if we can have a show of hands before we break. How many people are ready to show something today? 2 people are ready. Okay, great. Well, since it took me a long time to go through the homework, I hope the homework, going through the homework in this much detail makes it, Antonio 3. So I hope going through the homework in this much detail helps people who are having maybe a little more challenging to get replicating, thinking about how to do that replication. So, okay, so let's take our break. We'll say 6:47, 6:50. We'll take an 8-minute break. How about the people who are going to be demoing can get their computers loaded up and be ready for demo. Then you tell me when to screen share with you, and I'll set it up for you, okay? So I'll see everybody back in a couple of minutes. Get your coffee, stretch your legs, and I'll see you in a few minutes. Okay, are people ready to get back and talk about projects? So there's some parameters. It's still not, this oscillations are still decaying, but they look like they're a little bit more well behaved than they might have been. So. Explore those if you feel like it in your homework. Okay. All right. So who would like to present some results for their project? A bunch of people raised their hands, so.
I can go ahead.
Great, thank you. Antonio, take it away.
So I decided that I wanted to try to do something with antibiotic resistance as the problem I'm going to try to tackle. And so specifically, I think I'm going to take a look at tuberculosis as the disease in which I'm going to try to apply some antibacterial things to. And so here I've taken a paper by Abu Radad et al. And I'm trying to replicate his model of tuberculosis first and then kind of build on it. I had to simplify it a little bit. He age stratified it, and he had a fast and slow progression of the disease. I decided to make it a little simpler, and I'm just going to assume that they're all adults and it's all fast progression. I'm also assuming that I'll go through first. So you're starting with a susceptible, and then susceptible goes to latent, then transitions to early. And then once you're kind of in the early infection stage, you can recover, you can go into you can be identified and be treated, or you can go into any of the three categories of late infection. The first one being smear positive, the second one being smear negative, which has a 1/4 infectivity as the smear positive, and then the non-pulmonary, which isn't infective at all. And then obviously these can all go to recovered through spontaneous recovery, or they can go and be identified as treated, and then you can proceed into the recovered. So some of the other assumptions I'm making is that there's no spontaneous recovery in the early infection, and that only those in the treatment, the smear positive and the smear negative group, are infectious. And this data has all been calibrated against WHO TB incidence and mortality data for TB prevalent regions. So a lot of African nations, some Asian nations as well. These are some of the parameters that I'm using. I tried to split them up in kind of the different groups of parameters. I don't think I'm going to go into much depth of any of those there. They were all given as yearly rates in the paper, and so I've turned them into daily rates for the purposes of this. Okay, so I really just started roughly displaying the results. I think I still need to kind of beautify it a little bit, clean it up. But since there's so many different labels in this,
Right.
and they're all kind of on different time intervals, so I kind of just graph them separately. So susceptible transitioning to latent transitioning to early infection. And then these are just the populations of the late term infections over time. I should bump that up, that time range. And then there's some more. And then I started scanning through the paper actually never specified a contact rate. It claimed to in one of its appendices and then didn't list it in the appendices. So I looked really hard for it and they just never said anything about it. But I decided to scan through that to see what kind of results I'd get. And that was the contact rate. And it doesn't do much. It shortens that kind of cross between susceptible and latent period by a little bit. So the other one that they didn't list, I think this is the one, successful treatment rate. Yeah, they never listed this either. I don't know if that was just an error in their reporting, but they didn't even reference like another appendix for this. So I decided to scan through that too and see what happens. And as you increase the successful treatment rate, so that would be part of the people that you're identifying for treatment. So it's comprised of the rate at which you're going to identify people times the success, your treatment success, and that'll determine how many people actually get sent into the treatment label. And as you increase the successful treatment rate, more and more people get sent into that treatment.
Well, that's that's a lot. And it's always hard if they don't publish the results. I mean, I originally wanted to use that Goyal et al. Paper as the thing we were going to build the course around, except they don't publish their parameters.
Right.
Gilberto in Brazil spent weeks trying to replicate their results because they publish about half of the parameters you need. Half of the parameters that are essential to their model are not in their paper.
Right.
So this is really a great model, and tuberculosis in particular is a disease that's been modeled quite a bit, although maybe not as much as it deserves. I think I mentioned years ago being on a panel with somebody who was the head of basically the Office of Public Health, the head of Office of Public Health for a fairly large state. And we were looking at something about tuberculosis, and the guy said, well, I don't think tuberculosis is important to model because nobody gets tuberculosis, which was a really scary coming from a public health officer, because tuberculosis, as you know, has become very multi-drug resistant in many countries.
Right.
And one of the reasons for that is it's very hard to eliminate. Even with the best treatment, even non-drug resistant tuberculosis tends to form cysts in your lungs that last as long as you live. Your immune system keeps it in check, but you never get rid of it.
Right.
And so it's like HIV, a disease you don't clear. It's not that you never clear it, but the success rate of treatment is not 1. It can be actually fairly low, depending on how it's given and what the drug is. And then the development of resistance is very high, because if you treat and the disease is eliminated completely, the likelihood that the drug is that virus, that bacteria now is resistant to that antibiotic is quite high. And so you do have the situation where you have more and more antibiotic resistant tuberculosis. And people have forgotten that in the 19th century, a very substantial fraction of the population died of tuberculosis. It was called the White Plague. And it was called the White Plague because it was untreatable and it was lethal. And it killed, the order of 10-15% of the population. It wasn't a fast disease. It was a slow disease like HIV today. But it was really serious. And if highly drug-resistant tuberculosis spreads the way it did in the 19th century, we really don't have any good fallbacks for having to deal with it. And so I think you're addressing something that's a really critical point. In the developed world, TB is often the resurgence of TB was associated with AIDS, because what happened was it was cryptic, it was around, but people didn't notice it so much. And then when you started having in the 80s large epidemic of AIDS, which was associated with large numbers of people being immunosuppressed, you had big outbreaks of TB, lethal TB in New York, in San Francisco, in places that were highly affected by the AIDS epidemic. It's still much more prevalent than it was 50 years ago in the United States. And again, you could be immunosuppressed for other reasons. You could be immunosuppressed because you had an organ transplant. You could be immunosuppressed because you're on cancer therapy. And so in those situations, tuberculosis that's latent can break out and kill you. And it can be, when it breaks out from a dormant phase, it can be lethal very quickly. And so there are really a whole bunch of very, very interesting issues which you could model. And so I'm pleased that you've selected that as a topic, because I think there's a huge richness. Denise Kirschner has done beautiful spatial models of tuberculosis, how it forms cysts and how it resists antibiotics, because there are structural factors that allow TB to resist antibiotics, as well as they form biofilms that are antibiotic resistant. And so it's actually, I think, quite fundamental. One of the things that I think I mentioned early on, which is there was a news item I thought I sent around, maybe I didn't, one of these factoid news items in these digests, is that there's been a vaccine for tuberculosis for 75 years. And that vaccine is given to everybody in France. It's required as a childhood vaccination. They've actually, I think, just changed it, but they did until very recently required. In the US, it wasn't even available. You couldn't get the vaccine even if you wanted it. The main reason, as far as I could tell in the United States, was that the antibody test that And of course, with the context of COVID, testing has become very, how do you test? How do you know if you're positive or negative? So the standard cheap test for tuberculosis is an antibody-based test. And so if you were vaccinated, you tested positive. So you couldn't distinguish somebody who was actually infected from somebody who had been vaccinated. The US decided at some point that because the incidence was fairly low, it was more convenient to be able to have cheap testing than it was to vaccinate. And the vaccine efficacy was never fantastic. And how long it lasted, this was why juvenile versus adult was of concern, because it was a juvenile vaccine. Whole bunch of interesting things. The reason this has come up is that the factoid in the news release today or yesterday said that there may be some evidence that the Bcg vaccine for tuberculosis may be protective against SARS-CoV-2. In which case there'd be an existing approved vaccine that you could use, which could be rolled out immediately without all the testing and everything else. It seems mildly unlikely because the incidence rates and death rates in France, where most people have had this vaccine, don't seem to be any lower than they are elsewhere. If the vaccine worked, you'd expect that the R naught in France would be much lower than it would be in countries that didn't have it. And I don't think there's evidence for that. I didn't have a chance to read the article yet. But you might want to look into that because it's quite an interesting question. It would be just as remdesivir, for example, is a repurposing of a drug, antiviral developed in another context. The use of antibodies like the ones that Regeneron is developing. These are very old techniques. When I was a child, children were routinely given what were immunoglobulin shots, which are not monoclonal the way the Regeneron is, but basically polyclonal antibodies from adults to increase immunity. That basically stopped with the AIDS epidemic, because even though in principle these were purified, in practice there were enough children who were infected with HIV through improper use of antibody preparation, and there wasn't a lot of evidence that it worked very well. I think I mentioned also that I had this funny experience when we had these orphan kittens that we raised starting 4 years ago. 2 of them died. One of them got very sick. And a lot of your early immunity comes about through milk. So a lot of the antibodies were transmitted through milk. The kittens had been abandoned at birth, so they never nursed. So they were immunosuppressed. It takes time for the body's own immune system to turn on, as we know, or we'll know in a few days from looking at in our class, from looking at how the adaptive immune system works. And so our vet actually did it the old way. She drew blood from one of her adult cats, did antibody fractionation, and injected poor little Tiger, who was about this big, 5 days old, and sick as a kitten. I guess you can't say sick as a dog for a cat. With a series of antibody shots to get him through whatever the infection that did it his siblings was. And I can't say definitively that that's why he survived, but in fact, that technique is known. Again, those are polyclonal antibodies. Your hope was that whatever the adult cats were had been exposed to whatever the virus that this kitten had, and therefore there would be antibodies in circulation that were adapted to it. In the case of Regeneron, they're going after specific antibodies for SARS-CoV-2, which should be more effective. Something I didn't know, but talking to Tarun, who's a postdoc up in the med school, that antibodies have quite a long half-life. Most drugs, when you put them in your bloodstream, are cleared within at least within 12 hours, 24 hours. They don't have a long half-life. But antibodies do have a long half-life because they need to survive in your blood to work. Well, half-life is variable, though. It can be as short as half a day and as long as 3 months. I don't think it's well understood why there's that variability. So there's this whole series of very interesting questions that a study of tuberculosis and resistance and antibiotic, both resistance in the population, the sense of immunity, and antibiotic resistance in the bacteria bring up. And so I'm delighted that you've got that as a subject. I think it's fascinating. Which parts of that you decide to pursue is up to you, but it's a very rich field, and there are not that many. Given how important it is, there's been not as much done as it deserves. It's a very important subject. So that's great. Well, thank you. I hope, Antonio, keep talking to me, Josh, and others, because that's a great topic.
Will do. Thank you.
Okay, who's next?
I can go ahead and go.
Great. Tyler, please.
Okay. So I don't have a whole lot as of now, but I looked at this paper and it includes a model for delay, the 2 levels of infection where cells may not be producing virus, but they're still infected, and then when they're actively producing virus. So far, so this is the model for the delay with the eclipse phase. And like you mentioned earlier about some papers not posting parameters, I had to do some digging, and I'm not sure if I've selected the right values just yet, but so far this is the graph I have. And I did a parameter scan for beta and for delta so far. Excuse me. And then my other model, I haven't really gotten to produce anything yet, but it's basically just a simpler version of the previous model without the eclipse phase. And this is over influenza A.
Mhm.
And after I get this model working, I'd like to implement the immune response and see basically see how those two, how the immune response reacts with the viral load and how it clears or doesn't clear over time.
Okay, so let's take a look at your equations just for a second. That's good. So you have a birth process. So things going to S represent that E1 term is puzzling to me. What's happening in that E1 term?
Honestly, I'm not sure if I even expressed it correctly, but it's supposed to be the rate at which susceptible cells, I believe, become infected. It was a little confusing the way they laid it out.
Okay, so E2 takes care of that.
Right.
So E1 with a minus sign means that you have susceptible cells disappearing. And so basically what's happened there is that your total cell population is going down because S's are becoming I1s, and you also see minus. So that's effectively, E1 is behaving as a death term.
Okay.
It's basically taking cells out of the population. So I don't think that E1 should be there. One of the things that we face when we deal with antimony and the mass balance equations, which were right, where we have something going to something else, is that when it's written out as ODEs, sometimes one ODE takes multiple lines of antimony, and sometimes one line of antimony turns into multiple ODEs. And so E2 is giving you the rate of conversion from S going to I1. And so that's a rate equation for how S changes and a rate equation for how I1 changes.
Okay, I see what you're saying.
So you shouldn't need that E1 term there. Now, if you had cells being born, like new S cells coming because of cell proliferation, or new individuals coming to population because of births, then you might very well have nothing goes to S. But that would be representing the creation of new de novo susceptibles.
Okay.
Or for example, if you had cells that were individuals that were resistant that then became infectable again, which we did a little bit in our previous example from the homework, then that would show up there. But in general, just as a sanity check, there are a few sort of simple rules of thumb that you'll find in modeling, which is that when you have what's called decay, like S goes to nothing, representing death of cells, generally those terms look like constant times S. So death rates are typically called first order, because if you have no susceptibles to die, the rate has to go to 0. So you make it proportional to the number of susceptibles. Birth processes, nothing goes to S, where you have something S is appearing out of nowhere, generally don't depend on the number of S, because it's something else that's becoming an S. Now, if S is regulating it, then that bet is off. But a term that looks like beta times V times S going to nothing goes to S it could be true, but it's unusual. And so normally if you have an arrow with nothing on the left-hand side pointing at a variable, you expect that variable is not going to appear in the rate equation.
Okay.
If you have an arrow that goes, S goes to nothing, which is a death process, then you expect to see the variable S in the rate equation raised to just the 1 power, S times constant. And there's certainly going to be places where neither of those things is true. But the first expectation when you play with this kind of world for a lot is that that's what you'll see. And so the moment you see beta times V times S next to arrow goes to S, that raises a question. It could be right, but it raises a question because that's an unusual thing to see. Also seeing a negative rate is a little bit unusual because these equations are structured so that typically the forward rates are positive. They're not always positive, but seeing a minus sign there is also a little bit unusual. In the second term, where you have a conversion rate and then, so the second one also is a little bit unusual in the sense that you've got that minus K times I1 and then the K times I1 in the second one. And so what this looks like, which is probably what you did, which is you took the ODEs, which would have said ds by dt equals something, di by dt equals something, and put the rates from the right-hand side of those ODEs after your semicolons. And again, I'm not going through this to try to be critical of you. I'm trying to do it because this is something everybody does when they start doing this. And so I assume your classmates will have the same issue. This is why I'm talking it through. And when you start writing these rate laws in the form of S goes to I1, those have to be what are called balance terms. So you see here beta SV, KI1, KI1. Those kind of terms that you see there are typical when you write things in ODE forms. When you write these when you write these rate laws, those are taken care of automatically. So you don't expect to see these pairs. You'd expect to see K1, well, let's see, where would it be? I've got it wrong here. So if this is K1, K times I1, you'd expect to see this term here, but it wouldn't be there.
Okay.
The same way you see S goes to I1, that's fine, beta times S times V, this wouldn't be there. And so there's always a little bit of a trade-off, because when you write things in these mass balance forms, these transformation forms, they don't have quite the same structure as the ODEs. You can translate them back and forth, but it does take a little bit of practice to learn how to do that. And so one of the reasons I'm trying to work with some of the homework problems and with people in class in these examples is to try to give you some practice about that. And so I think what you've got so far is very good. But one of the reasons I want to see these now is so that if there's something like that going on, we can catch it and help you be more comfortable how to write it. And again, I guarantee that if you have an issue like that here, your classmates are going to have the same issue. Takes a little bit of getting used to write these kinds of rate laws in the form that we've got. But I think what you've got so far is great, and let's keep working on that and see how it goes. So Josh, maybe you can meet with Tyler and go over that a little bit and give him some extra help. I can do that too. Okay.
Okay. Thank you.
Does that give you some place to go with this?
Yeah, that helps a lot. Thank you.
Okay, great. Okay. Anybody else today?
I can go.
Okay, please take it away. And I hope sometimes people say that when I talk to them, they feel a little bit like they're a butterfly being stuck on a pin. And I hope my intent is not to put you on the spot, and my intent is not to grill you. I do try to take the time to help people understand things. And so if I come across sometimes as being brusque or pushing hard, it's not meant to be a criticism of you or your ability. And if you say, hey, that's not the helpful way of helping me understand something, I won't take it personally. I'll do my best to find a way to help each of you learn this material, which is challenging. And so if I'm not being helpful, it's okay to say that. Okay, don't worry about it. Don't worry. I'm not easily offended, and even if I am offended, I would never take it out on a student. I don't think Kali is going to be the person who's going to have this experience, but for everybody, I want you to know that the goal of this class is to learn together. If my manner isn't always what you need, feel free to tell me. Okay. So take it away.
All right, so the model that just a reminder, I'm working on a vaccine model for COVID.
Mm-hmm.
And this model that we're looking at today is an SV-IRS model from a paper that was originally published in a math journal. So it's a little more theoretical in its nature, but it's fine. I can still try to implement it. So we have our susceptible group, our vaccinated group, our infected group, and our recovered group. And even though there is no D specifically in this model, there is still death included in the model. So that's still there with this mu and D terms in our variables. So we have a bunch of different variables, which includes birth and death. Instead of a birth, though, they have this variable called A, which is recruitment of susceptibles into the population, and A is just added into S. So we have a bunch of other variables like vaccination rate, force of infection, inhibition measures taken by the infected, rate at which vaccinated individuals become infected, the treatment/cure rate, the rate of limitation of medical resources, the rate at which recovered individuals become susceptible again, the natural mortality rate, the disease mortality rate, and the recovery rate. And these values here are all values that they used in the paper. So that was.
And these are in your time units in years here, right?
Is it in years?
Looks like it.
Okay, I'd have to check on that.
If the mortality, well, no, if the natural mortality rate is 0.01, then you'd expect that the units would be years because your life expectancy is on the order of 100 years. But on the other hand, if the recovery rate's also 0.01, then then you would expect a faster. So it's worth. And again, if they were being very mathematical, they may not even have thought about what a reasonable time scale is. But that's an interesting question. In any case, the mathematical structure is fine. Okay, so please, I didn't mean to interrupt too much. I was just trying. I always, when I see parameters, the first thing I ask is what the units are.
Yeah, sometimes that's hard for this because like you
Right.
have variables like the treatment cure rate, which you might not always
Right.
know, the rate of limitation. I need to look in further into what these all mean, but
No.
I have a model to start, and these are the values that they use in the paper. I'd have to
Right.
look back if they specified a specific time frame for them.
Right. Right.
We have some initial conditions that I came up with because they didn't really specify in the paper, and we end up with a graph that looks like this.
Right. So you see a bump in your infecteds, then you see recovereds, and then the recovereds gradually go away because they go back to being susceptible. And it looks like for these parameters, everybody dies in the end.
Yeah, it looks like it. And we can't really tell what's going on with this vaccination curve either. It's just always pretty low, which makes sense given, I guess.
Right. Yeah, so sometimes just plotting that on a separate axis, if one of your variables has got a wildly different units, sometimes that's convenient. Okay, well, that's a good place to start. Looks like a perfectly interesting model. And the mathematics, I wished you had been on this call earlier today, this 2 p.m. call, because we had Bard Ermintrout on the call, who's all there every week. And he and Erica, the one who wrote that paper I sent around, have been working on this very nice in-host model of viral replication and immune response. And somebody asked him a question about why there was a term of the kind that there was in his model. And he gave a beautiful mathematical answer, which is that he wanted the immune system to have a bistable situation. You could either have chronic inflammation or no chronic inflammation. And he wanted the infection to lead to a high activity of the immune system followed by a shutdown going back to low level of inflammation. And he was able to say that means that the shape of the dependencies has to be this and this for purely mathematical reasons. And so he was able to actually write down, based on the mathematical structure that was required to give those results, a set of simple equations, and then able to then back out and say, well, what is it about the way the system works biologically that should give that? Now, we haven't talked in this class about null lines and stability analysis because I've been a little bit reluctant to do that because of the varied mathematical background. But it was a very elegant. Null-line plots are a very powerful technique, which are in Herbert's textbook, I think chapter 11. The old version was chapter 11. It may be chapter 13 now. I don't know how much we'll get to it, but it's a way of analyzing the mathematical structure of the equations. When I asked you the question in the homework about what parameter values, if any, give you stable oscillations, that would be answered using this method if you wanted to do it in a formal way. And so when people write these kinds of mathematical structures, like what you're seeing there, beta times S times I divided by I plus alpha, 1 plus alpha plus I, those kind of structures often come about from thinking about what we see are there's two, you either are sick, very sick, or not sick, and you don't stay in the middle very long. So how do we write rate laws that will promote those kinds of bimodal behaviors? So those are some of the kinds of mathematical questions that can be asked. We've taken a more operational, sort of more engineering approach to this, But these kinds of mathematical approaches can be very rewarding as well.
Yeah. Oh, and one more thing I should mention about this model. This was originally a time delayed model. So instead of having like just S and I here was S of like T minus some delay time tau and I minus some T, but that's a little difficult to do in Tellurium. So I just assumed a time delay of 0 just for now, I think.
Okay.
I know
So we could show you how to do the delays. Once you've got things set up, you basically do something like you do a bucket brigade. You say S now goes to S at time 1 goes to S at time 2 goes to S at time 3 goes to S at time 4. And so you wind up with a bunch of extra equations.
Okay.
But all they do is pass material from one step to the next.
Got it.
And if you do 4 or 5 steps, that's equivalent to a delay. And the time it takes to get through the system is 1 over the sum of the rate if the rate constants are K1, K2, K3, K4, the time to get through everything is 1 over parenthesis 1 over K1 plus 1 over K2 plus 1 over K3 plus 1 over K4. And so it's not complicated. It's not very pretty, but we can show you how to do that. So if we sit down together and look at the delays and you want to implement them, we can do that. Josh has done that in the context of some of the models we've done.
All right, yeah, that's something that I'd be interested in looking into.
Yeah. But I agree. The first thing is to try without the delays and see what happens.
Okay, so now moving on. This is the same model that we had before, but instead of using the parameters from the paper, I tried to, where I could, come up with some parameters that seemed more reasonable for COVID in the United States. So I just tried to estimate the number of births per day. I didn't take into account immigration because I didn't know how to find that information. I basically just took the number of births in the US in the year, divided by 365, and hoped that this would be reasonable. And then made some other adjustments, such as the recovery rate, which from what I found, people often, maybe not quite 2 weeks, but people tend to recommend being quarantined for 2 weeks. So there's some evidence that the recovery rate of COVID is like 1 week to 2 weeks, or like 10 to 14 days. So I went with 14 here. So again, some of these parameters have to be reworked, and then some of them we're going to be doing sweeps for down here, like for the vaccination rate. So keep that in mind. And then I found the total population for the US, estimates for the current number of infected people. So I'm starting at like 10 point now. No vaccinated people, obviously. And then we have an estimate of like 5.29 million recovered cases. So that's how I got these initial conditions.
Right.
So first we're going to sweep for the vaccination rate. We have a variety of values here. So obviously, as vaccination rate goes up, you start seeing this recovery curve decline a bit. I think all the curves decline a bit, but notably we'll start seeing some changes in this red vaccination curve, which makes sense. So we're seeing, I guess, the expected behavior that we want to see as vaccination rate increases.
Okay, so I can say right away, there's something slightly wrong in the way you've written the rate equations. And that is because the population and total population shouldn't be going to 0 so fast. Because effectively, somehow everybody's dying.
Yeah.
And so I think maybe, again, this may be a little bit like what we were talking about with Antonio, that when you took the ODEs from the original paper and turned them into antimony, maybe 1 or 2 of the terms are not quite what you think they are. And so one thing to do just to help us, I mean, we can certainly look at the paper with you. And Josh, maybe you could sit down and help her sooner rather than later. I can do that too, but tomorrow is sort of busy for me. Look at the paper and just make sure that the equations that you're implementing as written in the antimony are the ones that you want. So if you scroll up and look at the equation. So here, again, you have this written as S goes to nothing. So S goes to nothing usually means that your S's are dying. And then you have nothing going to S, which is a birth process. And let's see, V represents the vaccinated population, and I is infected. So I would have expected to see something like S goes to V or S goes to I instead of these separated equations. Now, if you just want to write ODEs, this isn't a bad way to do it. You can do it. But effectively, S goes to nothing and nothing goes to S are writing the same thing, which is ds by dt equals something. The only difference is S goes to nothing means there's a minus sign in front of everything. S nothing goes to S means this is positive. So this would be equivalent to writing, let's turn it into ODE. ds by dt, ds by dt equals minus, let's do the positive one first, A plus beta times R minus delta times S minus beta times S times I divided by 1 plus alpha times I minus I minus mu times S. So these first two lines, oops, I didn't to delete that. Those first two lines are equivalent to that one equation that I wrote there. And so that may very well be the equation you wanted, but if it's not, then we should double check and make sure that it is. One thing you can do is in Tellurium, you have markdown cells. So you could create above that first cell a cell which is marked down, and you could paste in the equations that you want. And that way you'd have them, you wouldn't have to jump back and forth between the original paper and here. You'd have them right there. And that's sometimes easier, just avoids eye skips when you're trying to do that.
Right.
And so again, I might, again, I don't have any particular reason to think there's something wrong here necessarily. And you do have you see again, what you've got here is what is a balance equation, which is typical of OD. So you have delta S disappearing because you've got delta times S, and it turns into V. That's fine. That means that, so delta is the vaccination rate. So that's a balance, but you might write that instead as S goes to V, semicolon, delta, I'll just use the symbol delta times S. And that would get both of those terms. What you've written isn't wrong, but it makes it a little bit harder to understand maybe in this context. And so it's possible that when you converted it, there was a sign error or something like that in one term. It's easy to make those mistakes. But I'm just puzzled by, this one looks reasonable. This first one looks reasonable in the sense that your total population seems to be conserved. This plus this plus this plus this give you this initial value. So that looks all right. But some of the later ones, it looked like here, right here, you start out with 10 to the 8th people. At the end, you have nobody left. Everybody's died. And having everybody die of 100 days suggests to me something is wrong mathematically.
Right.
So that's again, why I wanted to go over this now, so that if there were little things like that, we could catch them together.
Yeah.
Try to
those differential equations,
Right.
making sure that they're right.
Right. And again, don't be shy about asking for us to look. And certainly don't. We certainly don't have to look over your shoulder, but we're happy to, if that would be helpful. If not, it's okay. I understand the desire to do things on your own. But if you get to the point where you're feeling frustrated because you can't see the mistake, a new pair of eyes sometimes find. I mean, again, this big paper that is still under review that we started writing in March, that TJ and Josh and some other people worked on, and they were all ready to submit it. And I looked at it and I said, something doesn't quite make sense. Let me look at the equations again. Here are the equations. We looked at the code, and there was a minus sign. Where there was a minus sign where there should have been a plus sign in one line of 4,000 lines of code. And every single result had to be redone. Every single result. So it happens. And I'm not laughing because of the pain. I'm not laughing at the pain Josh and TJ and everyone felt. I'm laughing because it's such a part of human nature to do that. And if you wrote the code, it's so hard to see. So, and again, I'm not saying there is a mistake here, but looks to me like there could be one place, for example, where there was one sign error. Okay. Okay, well, did you want to talk about other things, or is that for today? Is that good?
Oh, I guess the only other things I talk about were more parameter sweeps. So this,
Right.
I mean, it's not that much.
Right.
Only 3 values, but it rate at which individuals become susceptible.
Right. So there again, things seem to be conserving pretty well. Maybe a little bit of die-off at the end. And so if there is a mistake, and there may not be at all, it's a subtle one, because most of the time things do what you would expect.
Right.
Yeah,
all these look pretty similar, except
no.
there's a bit of downturn. Yeah.
Yeah, a little bit. And it's certainly possible that you have, if the death rate's a little bit above the birth rate, then that can happen.
Yeah.
So I'm not saying having people die off is wrong, but having everybody die off in 100 days is a little surprising.
Right.
I guess if it were Ebola, maybe. Okay, great. But that's good. That's good. That looks like you've made a lot of progress.
And then it looks like here we're having some more die-off as well. This is, I think, was the limitation of medical resources, which I'm still not 100% sure what that unit is, but all these graphs generally look pretty similar. And then there's some population isn't totally conserved either.
Well, I mean, maybe the population shouldn't be conserved. Since I don't know the paper in detail, I don't know. But again, my point of doing this is because everyone's facing the same issues when you're doing these things. And so I'm trying to point out some things that might be sort of sanity checks or ways of catching small things before they get there. Again, most of these, the population seem pretty well preserved. So if there is a problem, it's a subtle one. But that's great. All right. Very nice.
Infection, and then that's my update.
Okay, thank you. Okay, anybody else? We've got time basically for one more person if they want to go. I don't think it makes sense for me to start giving you a lecture. It's 7:42 p.m. Maybe we can think of this as sort of a midterm. I promised you not an exam, but maybe you had a little bit of an oral midterm. Does that make it better or worse? Maybe worse. You're not going to get graded for it, though. Anybody else want to show a result or two? I thought there were 4 people who raised hands. So there's one person who said they were ready and then hasn't spoken up.
I can show something.
Okay.
So this is for the neuron model.
So is this Hodgkin-Huxley or something that looks?
It's here. right now I have these two equations
Mhm.
and this one.
Mhm.
So this was a first kind of attempt. I have these activation functions up here in these equations.
I can tell you right now that won't work.
Yeah, I don't think. Yeah, I
So-
got with this plot. Yeah, so that didn't work.
So there's a simple syntactical thing with Tellurium, which is an annoyance, which is if you have a function that depends on a variable like that, m calcium equals something as a function of v,
Yeah.
and you want m calcium to change in time, you have to use colon equals rather than equals.
Cool.
So you need, so just the way in Python equals is an assignment, but double equals is evaluate equality. Colon equals it says that this is something that has to be updated. Yeah. So why don't you try that? See what happens.
So it looks a little different.
So an equal sign is evaluated only when you do TE load A, and those values are never reevaluated during the run. Whereas colon equals is basically like writing a differential equation. It's telling you that it's a function that is continually changing.
Okay. Yeah, that helped a lot actually with this orange curve.
Is that meant to be an action potential?
The orange one is the blue one is an action potential, so
it has the right shape for an action potential.
The orange one is the percentage of open potassium channels, so it looks like it is correct. Also, it's a little bit delayed after the action potential. But the green one is I'm having trouble with still. It's the inhibitory potential. And it looks like it just goes up and then flattens. And I think that inhibitory potentials are supposed to dip down rather than go up like this. So I'm still trying to figure out how to plot this one. This was another attempt at trying to figure out, but I think the colon equal sign worked. I was trying to put these functions into these equations here.
Well, you can certainly do it that way. That's nothing wrong with that.
Yeah, so that was another attempt. This is pretty much all I have.
So it looks like they actually agree. So now they agree pretty well. So, okay. So we can, again, if you like to sit down with us, we're happy to go through it. I would recommend also doing this thing with the Markdown cells, which is create a Markdown cell above the thing and then paste in the equations that you're trying to replicate.
Okay.
And you can even put in a figure of what you expect the results to be. You can paste figures into. And that way you've got something right there, so you don't have to refer back and forth to your source material.
Okay.
All right, good. So we can do a little more on that as you like. Just tell us what your availability is.
Okay.
Okay, great. Well, so the people who did not present today, please do try to be ready next week. Do people think they want to try to take some of the things we did and rework the homework 5, or are you sick of homework 5 and you don't want to see it again?
I'd like to try to rework it.
I'm gonna go back and yeah.
Okay, so then the main homework will be keep working on your projects, rework homework 5. Josh, maybe from last week, from the beginning of the in-host model, could you write up 1 or 2 problems based on what we did last week? Because we didn't do an assignment so that you'd have time for this, but we did cover that material. So we may give you 1 or 2 simple exercises based on last week's lecture. And then next week, we'll start out going over people's projects and questions, because that really is the most important thing. If you leave the course able to take a paper and replicate it and understand it, then the course is a success. To me, whether you can do a specific homework problem is not so interesting. The homework problems are only there to help you get the confidence and ability to be able to do that project. Okay, and then we'll finish up the viral replication model next week. And then the next week after that, we'll try to have an example to do together for a replication problem. Any questions before we break? Everybody okay? We can stop a few minutes early, I guess. It's not a problem. Unless somebody pressingly wants to present their work as well this week.